So we're going to start by talking about basic collection concepts. The idea of a collection is, we have a variable number of like objects that we want to store together so that we can kind of perform bulk actions on all of them and keep them all together in one place. So the idea here is we can make, we start with arrays, right? But the problem with arrays is that they're a fixed size. So you need to know how many of these objects you're going to get. And if you know exactly how many of the objects you're going to get, then arrays are great and they're very efficient. But most of the time that's not the case, right? So we need collections because they can grow and shrink dynamically. So we're going to talk a bit about basic collection concepts in these slides and the next ones as well. So this is really the backbone of the course because data structures and collections, they're not exactly the same thing, but there's a lot of overlap there. It's like a Venn diagram where the two circles are taking up a whole lot of the same space in the middle. So if we understand the basics of collections, then, switching over to more advanced types of data structures is a little bit easier. So in C#, there's a group of classes known as collections that provide functionality for grouping and storing items of all types. Within the umbrella term of collections, we have stacks, queues, lists, hash tables, and other types of objects. We're going to look at some of them in the class. Most of them have very similar ways that they work. That is by design. And you'll see that when we get into writing our own custom collection, that we want to follow along with those rules as well, because programmers, like everyone, enjoy working with something that feels familiar. So if every collection has a method called add, and you make your collection and you call it join instead, then whenever anyone uses that object, they got to remember, oh shoot, it's not add, it's join, and that's frustrating. So we want to, when we make our own custom collections, to try to follow along with the conventions as much as possible. So we're going to talk about how the collections are similar and how they're different. But essentially, when we define a collection, most of the collections implement the same interfaces. So last year you studied interfaces and how you can create essentially a list of rules that you can apply to various classes so that all of those classes implement the same members and implement the same kind of methods and functionalities. So the interface, that's a structure that contains only signatures of methods and properties. Because it doesn't implement any functionality, what it does is it just says, okay, if you're going to be of type X, then you have to do A, B, and C and follow these rules. So it's meant to be inherited and define certain things that child classes must have. So the interface, well, there's a couple that we're going to look at, but the first one is iList. Usually interfaces start with an I, just to indicate that it's not a typical class. The iList interface represents a collection of values. So any of the classes that implement that iList interface have to follow the rules of that interface, which means you have to have an add method, you have to have a clear method, you have to have a remove method, you have to have a count property, you have to have the item operator for indexing. So that's why all of the collections under the iList interface work the same way. Now, the way that they implement those methods and properties might be different. So for example, if you have a list, the list add method adds the new item at the end. But you can write a method called backwards list and specify that the add method adds the new item in the beginning. Or you could specify you want a sorted list. And the sorted list, when you call its add method, it adds it in sorted order. So even though they all have an add method, the implementations of those methods are different. So some classes that implement iList, the array object class, array list, list, string collection. These are just a few of the more common ones. There are others. So you'll notice here that list is under the generic namespace here, where array list isn't. Now, the difference there is whether or not it's type safe. And we'll talk a bit more about that in a minute. Another interface that we commonly use is iDictionary. And iDictionary is similar, follows a lot of the same rules. You know, you still have to have an add method and account method and all those, or account property rather. But the difference is that it represents a collection of key value pairs. So instead of just having a whole bunch of objects, it has a whole bunch of objects, but each object also comes along with a key. So we're going to do some demonstrations of how to use key value pairs in an iDictionary type of object. And certain ones that implement that interface are hash table, sorted list, dictionary, list dictionary, and hybrid dictionary. So again, you'll see that dictionary is in the generic namespace, whereas hash table and sorted list are not. And then we've got other types of collections that are not part of either one of those two interfaces. So we've got stack and queue. Both of those we're going to study quite a bit coming up. Bit array and name value collection. So we're going to start by talking about a list. Now a list, sometimes it's referred to as a linked list, depending on who's coding it, is a collection of separate elements with each element linked to the one that follows it in the list like a chain. So the nice thing about a linked list, and I'm really kind of lamenting not being able to draw on a whiteboard at this point, is that you have all these objects and they could be the same type, they could be of different types. Now most of the time we want to keep all of the objects of the same type together. In order to put them together in a collection, what we do is we just chain them together. So for example, this first object here would contain a property that points it to the next object. And this object here would contain a property that points it to the next object. And so it continues on like that until you get to the last one. And it also would contain a property that points to the next object, but the next object is null. No, there we go. So a linked list is pretty versatile because the amount of data can grow and shrink dynamically. Certain types of lists can contain all different types of elements. You don't have to force them into one data type. The only real restriction is that each one needs to have a pointer to the next one. So the idea, the concept of a linked list is the most important building block for implementing other more complicated data structures. So this is the basics of linked lists. And from here, we can go to things like trees or graphs or doubly linked lists or stacks or queues. So our linked list is made up of nodes. On the previous slide, each circle represents a node. And what the node is kind of up to you. So there's basically two schools of thought here. Is that you can make a class, a node class, that has all the properties of the object that you want to store, plus the pointer. Or oftentimes you would choose to make a separate class representing the object that you want to store, and then your node would just have two references, the object and the pointer. So let me try to illustrate this here. Let's say I make a car class. Now I'm just visually going to try to draw a car object. There we go. Looks kind of like an El Camino or a spaceship. So here's my car object. And a car object would have something like, its odometer reading and make, model, year, color, all sorts of car properties. And if you wanted to have a list of cars, that one has a bit of a flat tire. If you want to make a list of cars, you would have a node that has two parts, your car and the pointer to the next node. So there's only two parts here. One is the entire car object, and two is the pointer to the next node. And then, each one would be like that, where you have the car and the pointer. So that's one school of thought. The other school of thought is that you can make the node class have all the properties. So let me, rather than trying to draw, I wish there was like a type on the slide option. Somebody needs to add that to PowerPoint. Type on the slide itself. Okay, so I've got my slides open here, and I'm going to put in a text box in this area, and you would have all of the car properties. Let me move this over a little so that it's actually inside the box. Here we go. So you would have the car properties instead. So instead of having an entire car object, you would have each individual property plus the pointer. So once we get all these things in order, the first node would need to be denoted. That's how we keep track of where we are in the list, because it's not like an array where every single one has a number attached to it. All we know about any given node is that here's the data inside it, and here's how you get to the next one. So it's almost kind of like a scavenger hunt, if you've ever participated in anything like that. You don't know your entire mapped out route. All you know is where you're going next. So you know where to start, and then you just follow the arrows until you get to the end. And the end points to null. So here's a much nicer drawing of it. And a linked list is what's known as a linear structure. And we call it a linear structure because each element has only one element before and only one element after. So it follows like a straight line. Some examples of non-linear structures are things like trees and graphs. So if we can say that, node A can only point you to node B, there's no arrow that you can go any different direction. That is a no. So that makes it a linear structure. Now here are some examples of a few more different types of linear structures, queue and stack. So list is linear, as are most things that we consider under that iList or iDictionary umbrella. All of these are linear structures because there's just one after another after another. So you can visually see that in these two pictures that I've put as well, that there's a straight line. It's not just a crowd of people all over the place. They're in a line. And same goes for these tennis balls. They're in a straight line. So we're going to talk a bit about queues and stacks. They are subtypes of linear linked lists. And they're known as constrained lists because they follow certain rules, and the rules are more rigid than in a typical list. So in a typical list, when you add items, you can put items in wherever you want. You can use add to add items to the end, or you can use insert and put items into the middle wherever you want them to be. But with queue and stack, that's not allowed. And so in these images, I've put up some pictures to kind of give you that idea that it's not allowed in a queue and a stack to insert items wherever you want. So the queue is like a lineup, right? And if you are a person here with no head or arms, then you want to join this line too, then you have to come in at the end, right? You'd have to come in back here. If you try to join the line in the middle, then these guys are going to be pretty angry at you. And you can't join the line at the front either. So there's a more rigid rule with the queue. Yes, it's a straight line, but it's constrained in the fact that there's only one place where you can add new elements, and that is at the back or at the end. With a stack, I've got the tube of tennis balls to indicate that. Now, if I wanted, this particular tube of tennis balls is full, but imagine if this top ball wasn't there, and I wanted to put another ball into the tube. There's only one place that I can put the ball in, and that's at the top of the tube. I can't put a ball in down here because this is not open at this end. I can't put a ball into the middle between two other balls. So the constraint of a stack is that you can only put a ball in at the top, or an object in at the top. Now what about removing things? Now in a queue, the only place where you can leave the list is at the front. So this is making sure that they go in order, and the first person who joins the line is the first person who gets to leave, and the last person who joins the line is the last person who gets to leave. In a stack, that's opposite. I can't take out this bottom ball if there's other balls on top. I can't remove a ball from any place except the very top of the stack. So with the tube of tennis balls, the first ball that you put in is the last one to come out. And that's opposite of the queue. If you were in a lineup and you were there first and then you were the last person who got served, I think you'd be pretty unhappy. But that's how it does work in a stack. So the queue is an ordered list where all insertions occur at one end. We call that the rear, and all deletions occur at the other end, which is the front. So the rules of the queue are you go in at the end and you come out of the front. The first element to be inserted will be the first one to be removed, and it's referred to as a first in, first out structure, like a lineup. So some of the operations that can be performed on a queue are NQ and DQ. Now, NQ is an add, and DQ is a remove. However, we don't use add and remove on a queue because add and remove have different connotations in a list. So we want to make sure that we have that clue that it works differently, which is why it has a different name. So an NQ adds a new item and always adds it to the rear. The DQ removes an item from the front. And there's no way to call like a remove or an insert or those other types of ones that you can use on another list to control where it's inserted or removed from. That's not allowed because that's the purpose of a queue. If you want to be able to insert or remove from anywhere, then don't use a queue, use a list. And then we have this peek, which shows us information about the object at the front, but doesn't remove it. So if you call DQ, the object is removed from the queue. But if you just call peek, you can see what's next, but you don't get rid of it yet. Then when we have stacks, stack is also ordered. All the insertions and deletions occur at the same end, and we call that end the top. So the very last one that's added is the first one that you remove. So that's, in contrast to the first in, first out of the queue. I'm just going to make a queue here. So queue is first in, first out, but stack is last in, first out. And the elements at the bottom are the ones that have been there the longest. So when we're working with the stack, the add is called push, and the remove is called pop. And we also still have peek. So push and pop with NQ and DQ are just specialized versions of add and remove. And then we move into nonlinear structures. So on the left, I have a nice picture of a tree here, and on the right, this is a picture of a graph. So the difference is, when you're in a linear structure, there's only one element that you can get to in either direction, before or after. If you have an element like this one, there's lots of different elements that you can get to. So a tree. A tree is a nonlinear structure because each element can have many successors, and we call it the children. Do I have an image of a tree here? No, I don't. So what a tree looks like is something like this, where the nodes kind of branch out. This kind of just looks like a weird spider at this point. But you can make these different kind of branches. That was weird. So the rules of a tree is that an element can have many child elements, but only one parent element. So when we go down the tree, you can have many branches pointing down. But when you're moving back up from any given element, there should only be one way back up. The element at the top, or the beginning, is called the root. I'm not too sure what's going on with my mouse at this point, but I'm trying to indicate that this one is the root. And the trees are useful when you have a hierarchy or an is-a relationship. So if you have like a person at the top, and then you have different subclasses of person, like you might have student and teachers. And from students, you might have like a part-time student and a full-time student. And from teacher, you might have like a tenured professor or a part-time instructor. So, they have, when you're breaking things down into more and more specifics, then that's one use for a tree. So a tenured professor is a teacher who is a person when you're moving back up, right? That's what that is a relationship means. So that's one way of doing a tree. Another example of a tree is something called a search tree, which we're going to talk about a lot in a couple months from now, where we can use a tree to sort the data in such a way that when we search it, we can search very, very quickly, because we can very quickly discard half of the data on every search iteration. And the graph, you saw the picture before, it's made up of elements and edges. So all the different ways of naming things, in a list, it's called a node, but in a graph, it can be called an element sometimes. And unlike in a tree, there are no restrictions on the connection between elements. And one typical use of a graph is for representing a map. So you might have elements that represent cities, and the edges or the connections represent airplane routes or highways. And you can start to calculate, like, if I'm in this city and I want to get to that city, which way can I go, and which cities do I have to travel through, and how much is it going to cost me, like distance wise. So there's all kinds of cool uses for trees and graphs. Okay, so now we're going to move into more of a practicality of dealing with some of these in code. So I'll stop the recording. We're done with that theory, and we'll look at some demonstrations in the next slides.